Hello there. So for today we will look into another subtopic which will be conservation of angular momentum. Okay, so for this subtopic, angular momentum we use symbol L. The definition is that the product of the angular velocity of a body and its moment of inertia about the rotation of the axis. Okay, so we will end up with equation L will be equivalent to I omega, which will be analogous to P equivalent to mv, where P represented by L and M represented by I and V represented by omega. Okay, so these are the definition for the symbol. Okay, and then the characteristic together with the unit and dimension. Okay, so for the principle of the conservation of angular momentum, state that the total angular momentum of a system about an rotation axis is constant if no external torque acts on a system. Okay, so that means I omega will be equivalent to constant. Okay, and then therefore net torque will be equivalent to 0 lah. Okay, the condition is that. Okay, so final momentum, okay, minus with the initial angular momentum, we should end up with 0. So therefore total initial will be equivalent to total final. Okay, let us look into example 8.1. Okay, over here you have a 200 kg wooden disc, radius given, rotating with angular speed of 4 radian per second about the rotation axis as shown in figure 7.2.1. Okay, and then you have a 50 kg bag of sand fall onto the disc at the edge of the wooden disc. Okay, so they wanted to calculate the angular speed of the system after the bag of sand falling onto the disc. They wanted to treat the bag of sand as a particle, and then B, the initial and final rotational kinetic energy of the system. Okay, and then the explanation whether it is same or not. Okay. So these are the information given. Okay, omega naught. Okay, mw will be the mass of the wooden rotating disc lah. Okay, and then mb will be the mass of the sandbag. Okay, the moment inertia of the disc. Okay, so using the equation already given in the question, we find the moment of the inertia of the disc. Okay, so we have a subscript w, that means wooden disc, which we end up with 900. And then for the sandbag, okay, we use a subscript of b, so mass given and then the radius also given, so we will end up with 450. Okay, and then by applying the principle of conservation of angular momentum, total initial momentum will be equivalent to the total final angular momentum. So initially we only have the wooden disc, and then after sandbag falls you will have the wooden block plus with the sandbag. Okay, so the moment of inertia you add up lah. Okay, before you only have one, okay, wooden block, after you have wooden block plus with the sandbag. Okay, so to determine the final angular velocity, we will end up with 2.67 radian per second. Okay. Okay, and then for the rotational kinetic energy. So kinetic energy we can use analogous to half mv square. So m we represent by I, and then v we represent by omega lah. Okay, so initial, so we only have wooden block, and then omega naught. So we end up with 7200. And then for the final, we have wooden block plus with the sandbag. Okay, so the total moment of inertia, that means wooden block plus with the sandbag. Okay, W and B. So we determine, so we end up with 48 and 4812 joule. Okay, now it is not equal. Okay, the reason is that because the energy is lost in the form of heat from the friction. Okay, between the disc and the sandbag. Okay, next question. This one you have a raw egg and a hard-boiled egg rotating about the same axis of rotation with the same initial angular velocity. They wanted to explain which egg will rotate longer. Okay, now the answer. You have the hard-boiled egg. Okay, for the reason. So basically, whenever hard-boiled egg rotates, okay, the yolk, okay, will remain at a constant position, okay, because the egg already has hardened. And then, whereas for the raw egg, it will start to move, okay, once it start to rotate. So the explanation we can see over here lah, the reason. So the raw egg, when the egg spin, the yolk being denser moves away from the axis, okay. So when it move away from the axis, okay, R will increase, okay, therefore I will increase. So since angular momentum constant, okay, so I increase, omega will become smaller lah, okay, omega will decrease lah. For the hard-boiled egg, the position will maintain, okay. This one I think maybe you can pause and then go through word by word lah, okay. Okay, and then for example 8.3, this one you have a student sits on a freely rotating stool, okay, holding two weight, each mass 3 kg, okay, shown as in figure. Okay, now what happened is that his arm extended, the weights are 1 meter from the axis of rotation, and he rotates with the angular speed 0.75 radian per second. The moment of the inertia of the student and stool is given, okay, 3 kilogram meter square, and it is assumed to be constant, and the student pulls the weight inward horizontally to a position of 0.3 from the rotation axis, okay, as you can see in the figure before and after. Now they wanted to determine the new angular speed of the student and then the kinetic energy of the rotating system before and after he pulls the weight inward, okay. So mass given, okay, initial angular velocity given, and then moment of inertia SS stool and student also given, okay. So rotation axis, okay, the perpendicular distance to the weight from the rotation of the axis, okay, and then this one for the after, okay, where the distance will become closer, which will be 0.3. Okay, the moment of inertia of the system initially, okay, so initially student plus stool, okay, and then the including the weight he is carrying, okay. So student plus stool, which will be constant, okay, and then add up with the weight he is holding, okay, mass of the weight, okay, which will be mr square. So the distance is 1 meter, so we calculate the total value, which will end up with 9, okay. And then finally what we need to do is that we have to recalculate again student plus tool, which will be constant. Now over here we will have changes in the distance because he pulled his hand inward. So the initial distance is 1 meter, right? Now it will become as 0.3, okay. So replace in the value, so we will end up with 3.54. Okay, so using the principle of conservation of angular momentum, total initial momentum will be equivalent to the total final momentum, initial times omega naught, and then final times omega. Okay, so we can determine the final angular velocity, which will end up with 1.91 radian per second. Okay, and then for the final part, initial rotational kinetic energy, okay, we use the analogous equation, kinetic energy half mv square. So over here will become half I initial times omega naught square. So we already calculated, or we already have the value in A, just replace in, okay, which will end up with 2.53. And then for the final, okay, we already calculated the final omega, replacing the value, and then calculate the final kinetic energy. Okay, that's all. Have a